Okay, so the topic that we will be discussing today is center of mass, stability, toppling, and how does that work. So before getting into stability and toppling and what exactly we are going to study today or what the phenomena are, it's important to really understand the concept of center of mass. So if we look at a body, we know that the mass that that body has, it has been spread in different directions, or that uh, the mass is evenly spread, or however, whatever the configuration is. But when we are doing some calculations, it is important for us to consider a force uh, that is a given force that will be given in every scenario, and that force is going to be the weight of that object. So a body behaves as if its whole mass were concentrated at one point called its center of mass. So when we are calculating the point where we consider that this force, that is the weight of an object, is going to act, that point on an object is called its center of mass or center of gravity. We can use both of these terms, they're the same, even though the earth attracts every part of it. Now, it's very important to note that center of mass is not a physically present point. It's not a point which is there, like there is this specific point where the weight acts. No, the weight acts evenly on the body because the weight is a force that is because of the earth that earth is applying on an object. However, when we are doing calculations, it is much easier to use this concept that there is this point where all of that weight appears to act. Now, there are multiple ways. Now, we cannot just assume one specific point as center of mass. There are some criteria and there are some experiments that we can run in order to find out what the center of mass of that object is going to be. So, the body's weight can be considered to act at this point. The center of mass of a uniform ruler is at its center, and when supported there, it can be balanced. Now, it is a very important experiment or a very important technique to basically find out where the center of mass of an object is. That the center mass of a uniform ruler is at its center. Now, the important word over here is uniform. That we can only say that its center is going to be right in the middle, only and only if and only the ruler that we are considering has uniformity or has even distribution. So wait, I'm gonna draw a ruler and basically show it out. So basically, if this is a meter rule, I'm not drawing it straight, but let's just assume that it was a straight meter rule because it's supposed to be straight. So let's just assume that it's a straight meter rule and it's a 1 meter, right? Now we know that its center of mass supposedly should be at 50 centimeters. So here we will have 50 centimeter. And as we can, if we like recall the concepts from our turning effect, then it's very easy to find a pivot point over here and then balance it. Like even if you put a finger over here, it will be balanced because what you're doing is that you're giving it a reaction force upwards that is balancing the weight force downwards. So that's why the ruler is going to be balanced. So basically you are giving the reaction force at exactly the center of mass. So they balance out. There isn't no turning effect. There is no force that is unbalanced. If it is supported at any other point, it topples because the moment of its weight about the point of support is not zero. So what happens is that the body's weight can be considered to act at that point, right? But if you don't if you don't balance it at that point and you balance it at some other point, then what happens is that the ruler topples over or that it moves or that there's a rotatory effect. Now what happens is that, wait, let me draw that scenario too. So this is a ruler that we have, right? But this is not looking good. It should delete this and draw another one. Okay, so here we go. So this is a ruler. This is the 50 centimeter mark. Okay, what you do, and we know that at this 50 centimeter mark, weight acts on it, right? Because that is the center of mass. Because center of mass is that point where the weight appears to act. So when we're drawing this body diagrams, free body diagrams are what they're called. So I can draw an arrow at that point, right? And when I'm taking the moments or whatever, then I'll take the distance from this point. So what if I don't balance it at 50 centimeter? What if I balance it over here? Now what happens is that the forces are balanced, right? Because the full forces are supposed to be balanced. Or, I mean, because even at this point, there will be some reaction forces, and so it will act in the upwards direction. Let's just say R, we're calling it R. And since the forces are balanced, it's not moving upwards or downwards or whatever. So we know that the magnitude of R is going to be that of W, right? Now, however, it's going to rotate. It's not in equilibrium, because for equilibrium, we need two conditions: that the resultant force should be equal to zero, and that the uh, and that the other thing, that is the resultant, what do you call them? The force and the resultant torque should be equal to zero. So in this case, the torque is not equal to zero, because the torque that is produced by R is zero, because it's right on the pivot points. There is no distance that is from that force. However, there is some distance from the weight force that is being applied at the center of mass. So that causes it to move. So that's exactly what it's written over there. Okay. So depending on the object's shape, its center of gravity can be inside or outside it. Now, if you think about it, you cannot imagine that. Why do we think that an object's mass, or the main, the accumulative mass, can appear outside the body? But what happens is that if you consider a hollow cylinder, well, I'm going to draw some diagrams. Let's just say this is a hollow cylinder. This is a sphere. Well, if you think about this affair, it's very easy to just think that right at the middle of this ball, the weight will be acting on. However, if you think about this cylinder, the center of mass acts over here inside the ring, which is not on the body, which is not inside it, which is actually um, outside it. Or even if you think about, let's just say, if you think about this, let's just say object or something like this, its center of mass will be somewhere here. Or if you think about this object, its center of mass will be somewhere over here. So the point is, the center of mass is just a imaginary term that we that on which it appears that the weight of an object is being um, applied. A meter rule is a uniform and irregular shape, therefore its center of gravity is at its center. A meter rule at 5 centimeter mark. The meter rule balances freely at its center of gravity. Okay. So now we are going to go through some examples of some shapes on which their center of mass is being balanced. So what happens is that if you think about this meter rule that we have already discussed, the center of mass of this meter rule is at 50 centimeter mark. So that is where it will be balanced, and a meter is a uniform and irregular shape. What if we have a meter rule which is like this, but it is 1 meter long? Well, then we cannot say that its center of mass will be at 50 centimeter. Its center of mass will be somewhere else. Like, we will have to find out through some procedure or through some experiment. So it's important to know that we are right now talking about regular shapes. So regular shapes have these symmetry mark that we can use in order to find out their center of mass. Now the disk, like if let's just say we're talking about a disk, a plate, a circular um, disk or something, the center of gravity is the center of the circle where the diameter crosses. So this is going to be the center of gravity or center of mass, which is written as point G. The center of gravity G is at the center of a ring where the diameter cross. In this case, however, you can see that we don't have a what do you call it? The center of mass is not on the body or not on the matter. It is outside the surface. It's in the space. It's in the thin air. So this is another example, but then again, because it was a symmetrical, it was a symmetrical shape. It was a symmetrical regular shape, so it was easier to just find out the center of gravity of it, which is the cross section. Oh, sorry, the intersection of these two diagonals or these two intersections. Diameter, sorry. Okay, now we are going to talk about irregular shape. Now we are going to talk about the irregular shape. And in this, we need to find out, we have like specific experiments that need to be carried out in order to find out the center of mass. Let's just say in this case we have an irregular shape, but still it's a shape that we know, which is a triangle. What if we have like a shape like this, or the hockey stick that is made over here? So let's just first discuss the triangle part. So what happens is the center of gravity is where the medians cross. Well, median is a line which goes from one edge, one point to the opposite edge, or like this. So this point to the opposite edge is right over here. So this point to the opposite edge is right over here. So the line joining this will be a median. This will be a median, and this will be median. And we can clearly see that there is this point where these all intersect. So this is going to be the center of gravity. A hockey stick is non-uniform. It is thicker and heavier on one end. Its center of gravity is not at its center, but it will be closer to the heavier curved end. So what happens is that you have to basically balance out the masses, right? So we see that, oh, it's not like a meter rule. It's not uniform. It is thicker over this end and thinner over this end. So even if it's like a 1 meter stick, 1 meter hockey stick, you cannot expect it for it to have the center of mass at 50 centimeters. It will be somewhere over here or here, closer to the bulkier, closer to this end where it has its, whatever this is called, the end where you hit the ball from, because that is more heavier and that has more mass in it. So basically what will happen is that the mass of this side will be equal to the mass of this side, and then this point will be somewhere, I guess, the center of mass. Okay, now that we have the concept of center of mass, now we are going to discuss the idea of stability. So stability is basically a measure of how likely it is for an object to topple over when pushed or moved. Stable objects are very difficult to topple over. So the more the stability, less likely to topple. So stability is a measure of how likely it is for an object to topple over when pushed or moved. Stable objects are very difficult to topple over, while unstable objects topple over very easily. An object will topple over if its center of gravity is outside the base or edge on which it is balancing. Now, this is very important. It really does not make sense when you read it at first, but I'm going to explain it to you through this diagram. So, in this first case, it says that the car topples. Now, we need to see that. Well, this point over here is the center of gravity. So we say that that over here the mass is acting right on this line. Now, this point where the wheel is at, this is basically the pivot point or the edge in which the car is going to topple over, right? Because if through which the car is going to uh, rotate. So basically, the car was like this. This wheel over here was initially over here. So this went like this. The wheel over here, that is, it was initially over here. It went over here. So now you can see that the arrow is not inside this part. It's not inside over here. It's not somewhere over here. It's not like this. It's outside this part. It's outside this. It's on the other side of this pivot point, right? Um, and however, on this case, initially the car was like this. This wheel probably was over here, and it went like this to this position, and it is balancing on this edge. And this arrow, the green arrow, is not on this direction. It's not on the what do you say, the left side of the pivot point or the balancing point. However, it is on the right side. It's inwards. It's over here. It's the right of the pivot point, which is over here. So that's why it won't topple over. So basically, you have to see that this is basically the outside inside theory of toppling over. For an object to be stable, it must have a wide base, because if it has a wide base, then it has larger area for the arrow or the center of gravity to be inside than being on the outside. So a low center of gravity, objects with a wide base and low center of gravity are more stable than those with a narrow base and high center of gravity. The yellow car has a wider wheelbase. Well, the yellow car is the one that we were talking about over here. It has a wider wheelbase, and its center of gravity is also a bit downwards. This is a very stocky, a very thick car, so its center of gravity is upwards. However, this one is more sleek and more wide with a wider base, so it has a center of gravity more downwards, hence it was more stable and less likely to topple over. The wheel acts as a pivot. The weight has a turning effect or moment which causes the car to topple. Okay, so yeah. So now we're going to talk about the movements and how they are going to work. So the car does not topple over, and it was initially like this over here. This over here it had the first wheel, and then there we had the second wheel, and the car was just standing here like this, and then it was pushed over or something, and then it formed this shape that it has right now in the diagram. And then because its center of mass, center of gravity is inside, is towards the right side of the pivot point, it will not topple over, and it will get back to its original place like this. Boom, it will get back. However, over here the center of gravity is towards the left side of the pivot point, so it's gonna, instead of getting back to its original place, it will go back like this. It will have an anti-clockwise moment. So A double-decker bus is stable as it has a low center of gravity because of its low heavy engine and a heavy bottom deck. Now, if you think about it, a double-decker bus, it has, two places where people can sit on the upper side and then on the lower side. It really sounds hard for it to make it stable enough so that it can really occupy people on both the decks. However, what they do is that they put these weights around it. They put these weights on the lower end of the car, which lowers its center of gravity, and you also can see that they are also very wide based, hence why they are still stable, although they are double decker. Traffic cone is also stable because it has a low center of gravity because of its heavy base and because of this wide base. So this base is also very heavy and it is also very wide. And then we have this shape which is in the form of a triangular cones that brings its center of gravity to the lower side. The terms are used in connection stability, stable equilibrium. A body is in stable equilibrium when it's tightly displaced and then released to its original position. Its center of mass rises when it's displaced, but it rolls back because its weight has a moment about the point of contact that acts to reduce the displacement. So the point is that it is in a stable equilibrium if you displace it, but then it is released back and it comes back to its original place. So that is stable equilibrium, that you can move it, that you can change its position, but then it'll come back like what do you call it, a pendulum or something like that. Unstable equilibrium, however, is when a body, like if you move an object, like if it moves further away from its previous position and it does not come back to its previous position. So an unstable equilibrium is when it moves further away from its previous position when slightly displaced or released. Neutral equilibrium, however, is when a body is in neutral equilibrium, it stays in its position when displaced. Even if you move it, it will not move and it will stay in its place. A center of mass does not rise or fall because there is no movement to increase or decrease the displacement. Now, there are some examples of this. Okay, now over here you can see that initially you moved it, it came over here, the ball, its center of mass rose, and then it came back to this place over here, and its center of mass came back to its original point. This is a stable equilibrium, this one. Okay, now this is unstable equilibrium because if I push it like this, then it goes downward and then it won't come back up to that original place. However, over here, I've moved my object, but still its center of mass remains at the same level, at the same point on the ball. So that is how it is. This is it for now for this topic.